Welcome to this tutorial session of the International Memory Workshop 2020. My name is Thibaut Devolder. I come from the Centre de Nanosciences et Nanotechnologies. This is in Paris-Sud, France, and I will talk about the STT-MRAM switching. I'll try to give you the key features of the switching and the modulation knobs that we can turn to change the performance of this technology. Most of the work I'm presenting here is the result of a very fruitful collaboration that my group at C2N and especially my student Paul Bouquin had together with IMEC Belgium and a group led by Johan Zwerts and Sébastien Coué. This is the outline of my talk. I will first spend a few slides presenting STT-MRAM in a nutshell, and in particular how do we read the information using tunneling magnetoresistance, and how we store the information using magnetic anisotropy. And after that, I will spend the first part to recall the dynamics of magnetization switching in an idealized STT-MRAM, which is the macrospin model, in order to introduce some of the most useful formulas for STT-MRAM and a table of typical magnetic properties. Then in the second part, I will go to more realistic systems, and I will describe how does the magnetization reverse in STT-MRAM cells. I'll first do it at zero temperature, then we will increase the temperature to see what changes, and this will help us to define the sizes in which macrospin switching happens and in which domain wall switching happens. And then I will show that the critical current in fact does not depend much on the switching path. And finally, from this understanding of the switching dynamics, I will discuss how to optimize the speed of switching and the energy cost of the reversal. And one of the conclusions of this second part will be that the main factor that we can play on is the damping parameter of the magnetic material of the free layer. And so this leads us to a last part of my talk, which will be the discussion of the damping parameter in cobalt iron boron MgO systems, which is a parameter that needs to be reduced and optimized. I will first describe the role of boron in this material and what is the reason why the boron content impacts in the end the damping of the iron cobalt boron free layer. And then I will discuss the benefit of dual MgO free layer, that is to say, free layers encapsulated by two MgO layers versus the more standard historical single MgO systems. And finally, I will discuss the detailed composition of the free layer and how they impact the damping of this free layer. And of course, at the end, I will summarize my talk. So spin transfer torque magnetic memories, STT-MRAM. The concept now dates from the previous century, and it was the idea that if you have a magnetic multilayer with a free layer with a magnetization that can be manipulated and a reference layer with a fixed magnetization, in fact you could define two different states depending on the magnetic orientation, and one would have low resistance while the other one would have high resistance thanks to the magnetoresistance of a tunnel junction. And in this system, you could switch the information by passing a large current perpendicular to the plane of the layers and harness the spin transfer torque that was predicted by John Shonshevsky some time ago in 1996. And there has been a lot of interest in the research on this technology because, as any magnetic technology, once you store the information into the magnetization degree of freedom, it's non-volatile, it stays there, and there's no need to apply some power to maintain the information. Then we soon realized that it could have a reasonable storage capacity, that it could probably be fabricated above the back end of line of CMOS, and that as most magnetic technologies, it's robust and endurant, so it can work in hot or cold environments. It's radiation hard, so it could work in space. But one of the questions that was very important to answer was whether this technology could be rather fast and rather low power. Otherwise it would not exist, and this is what triggered a lot of physical studies to understand magnetization dynamics. This technology get to a turning point in 2010 when it was demonstrated that we could do it with perpendicular anisotropy layers, that is to say layers that have a magnetization that is perpendicular to their direction, to their plane. Okay? Because by proving that, it made clear that the dimensions could be scaled down, because with perpendicular magnetic anisotropy, the magnetization was much more stable. So the concept was essentially to have two magnetic layers, most of the time based on cobalt iron boron alloys, that could be coupled through an MgO tunnel barrier, and one layer would have a free magnetization, so would store the information, and the other one would be fixed. Okay. Although this is the device concept, to make it work in a real product, there's many more requirements and material engineering needed, so that in fact the product in the end is much more complex than the device concept. And I hope after this tutorial you will understand some of the ingredients that are needed to go from device concept to product. So as I told, the reading in STT-MRAM is done by a phenomenon that is called the magnetoresistance, which allows the resistance of a tunnel junction to differ depending on the magnetization orientation of the layers. If the layers are parallel, then the resistance is generally low, and if the magnetization are anti-parallel, the resistance is generally high. And this is because in magnetic materials, the density of states of spin-up and spin-downs are different. So if you have two electrodes and you want to have electrons that tunnel from the top electrode to the bottom electrode, then if they have parallel magnetization, the majority electrons in the top electrode are also the majority electrons in the bottom electron, and so they can tunnel with a current that is proportional to the density of state of these electrons at the Fermi level. And also the minority electrons can tunnel, but if there are less, then it gives less current. If in contrast you reverse the magnetization of one of these two layers, then the spin-ups that were the majority electrons in the top electron are now the minority electrons in the bottom electrode. So this results in two currents, two spin-polarized currents that are different compared to the case of the parallel state. And overall, if you compare the amount of current flowing in the parallel state and in the anti-parallel state, they differ, which yields the magnetoresistance, which is essentially to first order proportional to the spin polarization at Fermi level inside the ferromagnetic electrodes. And so this was Giulio's model from a long time ago. Okay, and in this model, what matters is not the state of the electrons, but just their population at Fermi level. And so with standard ferromagnetic metals, if you look at the spin-resolved density of states, just like in iron here, you can see at the Fermi level, so this dashed line is the Fermi level, there are both spin-up and spin-down electrons, such that even the high resistance state, there will be some current passing, and in practice the tunnel magnetoresistance of this type of barriers is limited to no more than 80%. Okay, and this was the case for amorphous barriers. It was realized in 2004 and predicted some time ago by Butler and co-workers in 2001 that if instead of using an amorphous barrier you use a crystalline barrier, then you could get a much better magnetoresistance. And the reason is the following. If you have an amorphous tunnel junction, an amorphous tunnel barrier, then all electrons at the Fermi level can tunnel with the same probability if they have the same energy. It doesn't matter whether their orbitals are constructed from S states, P state or D state, they all tunnel with the same probability because the tunneling doesn't preserve the symmetry of the block states in this configuration. But if in contrast you use a fully crystalline tunnel oxide, Okay. Then the probability of tunneling of the different electrons within the electrode will differ and will depend on the symmetry of their states. For instance, if you have a delta 1 state, which is a state that is constructed from S-like atomic orbitals, then the S orbital extend to large distances, and so they extend deeper inside the tunnel barrier, so they will have a high tunneling probability. By contrast, if you use delta 2 electrons, so constructed from essentially d states, then the orbitals are much more localized, and so it's much more difficult to have overlap of wave functions between the two ferromagnetic electrodes, so that the tunneling current is low. Okay. But the good thing about the iron MgO iron system is that if you look at their spin resolve dispersion relation, you see that in fact at the Fermi level, the delta 1 states, so these states that tunnel easily, they are fully spin polarized. The majority band crosses the Fermi level, but the minority spin band doesn't cross the Fermi level. So these states are fully 100% spin polarized, so that you can get in principle a very high, if not infinite, magnetoresistance, provided you have perfect epitaxy inside the stack and perfect crystallinity of the barrier. Another good thing about this giant tunneling magnetoresistance process is that if instead of having pure BCC iron, you add electrons in the system by doping gradually with cobalt, what you will do is you will raise gradually the Fermi level. Okay? But even if you would do a perfect BCC cobalt, pure cobalt, then at the Fermi level, the delta 1 band would still be fully 100% spin polarized. So somehow any BCC transition metal alloys made of iron and cobalt will have the potential to have a giant tunneling magnetoresistance. Another thing that you need for STT-MRAM is to have a strong magnetic anisotropy that maintain the magnetization in a fixed direction to store the information. And in the material systems of interest for STT-MRAM, this is provided by interface anisotropy at the interface between iron, cobalt, and MgO. The situation is the following. The d orbitals of the iron-cobalt transition metals are in front of the p orbitals of the oxygen of MgO. And if you have the pz orbitals that are in front of the dz orbitals of iron-cobalt, and if they point towards each other, then there will be a strong hybridation between these orbitals, which will reduce this energy. And these type of orbitals carry the angular momentum. If in contrast, you look at the orbitals that are in the plane of the iron-cobalt layer and in the plane of MgO, in fact you see that because of the shape of these orbitals, there's not much hybridation, so there's no gain of energy for these orbitals, and they will be efficiently less occupied. Okay? And so because there is some locking of the momentum and of the angular momentum and of the spin because of spin-orbit coupling, these orbitals that will be less populated will carry less orbital moments than these orbitals. Okay. And most people remember from their classrooms the Brunel's model of anisotropy, which expresses that the anisotropy energy of a magnetic system depends on the spin-orbit coupling times the anisotropy of the orbital momentum. So how much the orbital momentum varies when you rotate the magnetization. And so as you can see, this situation of iron cobalt MgO is very favorable for interface anisotropy because you expect a strong anisotropy of the angular momentum. Last thing that I want to say about the interface anisotropy is that to have this interface anisotropy, essentially you need to have the correct stoichiometry at the interface, because you need to have these p orbitals of the oxygen of MgO be in front of the orbitals of iron cobalt. So this requires a sample where not only you have perfect epitaxy, which is needed for giant TMR, but you also need to have the correct stoichiometry at the interface to get this strong interface anisotropy. Something that I want to mention, but I will come back to this problem later, is that in fact the total anisotropy is the sum of the interface contribution, but also minus the demagnetizing energy. That scales proportionally with the thickness of a magnetic layer and the square of the magnetization of the layer. So in principle, if you would just look at this sole criteria, you would like to avoid large materials with large magnetization and that are thick. Okay, so we'll come back to that, but it would be an argument not to use iron, cobalt, boron alloys. But we'll come back to this. So as I told you, the concept of STT-MRAM is to have an MgO tunnel barrier that will provide the magnetoresistance and the spin torque effect, and cobalt, iron, boron free layer, okay, plus a reference layer here in green. Okay. But this is the concept only. In fact, to make it work, you need many magnetic layers, and this is, for instance, a stack that was published in 2013. At that time, it was not the there are much better stacks now, but I want to comment on this. What you can see is that in addition to the concept, there are additional layers. So especially there's a very thick reference layer and a very thick hard layer, whose magnetizations are supposed to be coupled anti-parallel through an antiferromagnetic coupler, here the ruthenium layer. And because the stack is such complex, if you anneal the system at too high temperature, the structure degrades and the performance metrics goes down. And for instance, at that time, you would typically have a free layer with 200 millitesla of anisotropy, a damping parameter of 2 × 10⁻², a TMR of only 100% with an MgO barrier that is fragile. You would have a reference layer that would maybe not be coercive enough or stable enough, which induces problems of backhopping, and the hard layer would not provide enough moment to compensate the moment of the reference layer. So this triggered a lot of problems, and I'm just listing a few of them that we had to solve in the latest year. First, if the magnetization of the hard layer and the reference layer are not properly compensated, they generate a big stray field on the free layer, such that the hysteresis loop of the free layer is non-symmetrical. And for instance, in this extreme case, there's only one state of the free layer that is stable in zero field. Okay, so this is the state of the low resistance state. Then another problem was that the reference layer was not stable enough. Okay, so it was static for one switching direction, but not static for the other switching direction, which yielded a lot of problem of backhopping of the magnetization. And finally, the TMR junctions at that time was not strong enough, so they were fragile against dielectric breakdown. So after using the memory for some time, the resistance was dropping to almost zero because the MgO barrier was destroyed. Okay. So a lot of problems have been made, and a typical high-performing stack nowadays would look like this. So now the free layer is on top, while previously it was at the bottom. Okay, but if you look at the performance metrics, you see that now you can have free layers with typical anisotropy fields of 600 millitesla instead of 200 millitesla, with a much lower damping, so that they would switch for a voltage that is less. There would be much more magnetoresistance. It would be more robust to break down, and also the reference layer and hard layer would be much more stable. And the material engineers and the material scientists have managed to optimize these stacks so that now it's fully 400% degrade compatible before any degradation happens. Okay, and in this talk I will try to give you a feeling on how it was achieved to get this high anisotropy, low damping and annealing capability, and why there was so much effort focus on performing this matrix. So the first part of my talk will be to look at how the magnetization would switch in a very idealized STT-MRAM. So this will be essentially about the coherent reversal induced by spin transfer torque in the macrospin approximation. So if you want to study that, you do micromagnetic simulation, and let's do it for a start for a disk of 20 nanometer diameter, and I will apply a voltage that is just above the switching threshold at 0 temperature to have the magnetization pass from white, which is pointing towards you, to black, which is pointing towards the blackboard. And so we plug in the spin torque at time 0. And what happens is that after some time, the magnetization starts to precesses and finally switches. And if you zoom at what happens during this time scale, this is the Z component of the magnetization and the in-plane component, you see that the magnetization makes a growing precession until so it's spiraling out of the North Pole until it passes the equator and finally converges to the South Pole. And for this size of tunnel junctions, so 20 nanometer diameter, if you look at the magnetization all along the evolution, the magnetization stays extremely uniform. So the total moment stays very close to 1 all along the switching, and if it stays very close to 1, you can assume that all spins behave the same and model this reversal in a macrospin approximation. So the macrospin approximation is that you just consider one big spin that would describe the full system. And the good point about this macrospin approximation is that it can be solved exactly. Okay. And so if you rewrite the magnetization dynamics equation, the LLG for a macrospin with perpendicular magnetic anisotropy submitted to spin torque, then the rate of change of the magnetization is proportional to a few terms. One of them is this time constant tau, okay, which is the natural time scale of the switching, which is the reciprocal half line width, so this is the inverse of the product of the damping parameter and of the anisotropy. Okay. So that's the first term. There's the natural time scale for switching of a macrospin, which is the reciprocal of the FMR line width. Then there's the second term, which contains this red term, V, which is a generalized stimulus, and if you don't apply any magnetic field, this is just the voltage over the threshold voltage. Okay. And so the good thing about that is that it can be solved exactly, and if you compare for a 20 nanometer disk, the time response of the magnetization in an exact micromagnetic simulation or in a macrospin simulation, they are extremely similar provided you properly define the switching threshold and the anisotropy field. So it's interesting to have this macrospin model, okay, because in this macrospin model many things are analytical. Especially, in particular, the voltage switching threshold Vc, okay, which is the product of a few terms. There's the first product is this red alpha over P, where alpha is the Gilbert damping of the free layer, and P is the tunneling spin polarization. Then there is the resistance area product of the junction, its magnetization, its effective anisotropy, and its thickness of the free layer. And if we take typical material parameters for dual MgO free layer, here on the top left, this is a magnetization of the order of 1 Tesla, okay, and a damping factor of the order of 10 to the minus 2. And if you take the typical material properties and calculate the typical switching metrics, you see that in practice you expect a junction to switch at typically half a volt and to have a natural timescale tau that is a fraction of nanosecond, from 1/3 to 1 nanosecond. And if you go on applying the macrospin model, a good thing is that you can calculate a lot of things analytically, in particular the error rates the switching speed and the thermal stability, and there's a very good review of what you can do in this paper by Butler and co-workers in 2012, where they calculate the right error rate here as function of the voltage over the switching voltage for a given cell. So much for the macrospin, the switching threshold of it, and the natural time scale. Now I will come to the more realistic systems, which are the STT-MRAM cells. Okay. So previously we calculated the magnetization dynamics from a 20 nanometer, and the magnetization was coherent from the start to the end. If you make the junction slightly larger, so 22 nanometer, then you see that during the switching the magnetization gets no longer uniform. There's first a uniform stage, and then the magnetization gets non-uniform. And if you go to a wider junction, so 40 nanometers, in fact, after a macrospin stage in which the magnetization stays uniform, you nucleate a domain wall, okay, and the domain wall sweeps through the device. Okay, and so if you decompose the switching of this 40 nanometer disk into these two steps, first coherent phase and then a domain wall based switching, and if you plot the magnetization versus time, for the macrospin approximation in black and for the real system in red, you see that as long as the magnetization stays uniform, you can describe the dynamics with the macrospin, but after that, you see that the domain wall-based switching is substantially slower than what the macrospin did. So the switching is in many cases induced by in all cases induced by the instability of the uniform state, but it can involve domain wall based mechanism as soon as the system is large enough. So at larger sizes the reversal becomes more complicated with sometimes several domain walls into the system. But what is very important is that anyway, to get the switching, you need to destabilize the uniform state. So to get the switching, you need to have a voltage that is equal to the critical switching voltage of a uniform magnetization, which is the macrospin model. And if you plot here the switching threshold versus the size, the diameter of the STT-MRAM, in fact, you see that it always fits with the macrospin threshold, even when the magnetization reverses in a very non-coherent manner. So the macrospin switching voltage, VC, is an interesting concept, even if the magnetization stays non-uniform. So this was what was happening at zero temperature, okay, where the magnetization at small sizes was staying very uniform. If instead of working at zero temperature we work at room temperature now, in fact, if we look at the snapshots of the magnetization, there will be some disorder in the magnetization, but still if you look at the overall total moment, you see that it stays close to 1. So despite the noisy magnetization patterns, the magnetization stays rather coherent for these small sizes, even at room temperature, during the switching. If you go to larger disks, so larger STT-MRAM, so 40 nanometer and 80 nanometer, and once again you do the calculation at room temperature, so you heat the tunnel junction, you see that you see in these snapshots taken during the magnetization reversal that it's still a domain wall process. So the way the magnetization reverses does not change, but there is a stochasticity. So each switching event will take a different time. So these are eight different simulations at room temperature, and you see that the time it takes for the magnetization to switch varies. But if you group all the curves together, you see that what varies is the initial delay before the magnetization switches, but it seems to always switch about the same way using a domain wall process. So the size at which we have a uniform reversal or a domain wall based reversal can be deduced from energy considerations. Because if you compare the energy barrier for uniform magnetization reversal, then the highest energy state during the reversal is when you have the magnetization in the plane. So this is proportional to the cell volume times the volume shape, the volume anisotropy. And if you have a domain wall process, the maximum of energy during the reversal is when you have the domain wall along the diameter. So the energy that it costs is the wall energy per unit length times the wall length, which is the diameter. And in fact, these two energies cross each other when you have a cell that is typically a few times the block wall width. Okay. So in practice, you can do it in a more rigorous way by calculating exactly when this crossover happens. So the critical diameter will change with the anisotropy field and with the exchange constant of the magnetic metal. But essentially, if you take a junction that is 25 nanometer diameter, for any reasonable material parameter, it's always going to be a domain wall-based reversal. So this is one of the message. The macrospin reversal doesn't exist, although the macrospin threshold is a relevant quantity, and magnetization will always or almost always reverse by a domain wall process. So let's try to discuss anyway how to optimize the switching speed and the switching voltage. Okay. If you look at the switching voltage, essentially if you want to reduce that, to reduce the energy cost of your reversal, then you can play on the alpha over P parameter, so alpha being the Gilbert damping and P being the spin polarization. And as I told you, the spin polarization is almost 1 already, so there's not much you can gain on this side. And so what you can gain is by reducing the damping parameter of the free layer. You can also gain by reducing the resistance area product of the junction, that is to say making the junction thin, the MgO layer thinner. Okay. But you're not allowed to reduce the product of the magnetization, anisotropy and free layer thickness, because this somehow sets the energy barrier. Let's look at the switching time first for a macrospin, and then we will do it for a domain wall-based assisted switching. So if you have a macrospin, then the magnetization at time 0, before you plug in the spin torque, is not along exactly the easy axis because there are thermal fluctuations. So the magnetization is typically tilted away from the easy axis by an angle delta theta, which is a compromise between temperature and energy barrier. But it's definitely, this delta theta is not 0. It's typically a few degrees of standard deviation. So if from this state you plug in the spin torque and you look at the subsequent time evolution, then you see that the rate of change of the magnetization will depend on the natural time scale 1 over tau, the overdrive, that is to say how much voltage you apply in excess to the switching threshold, and how much the magnetization was initially tilted away from the easy axis. Okay. And so you say that this gives you immediately the order of magnitude of the switching time, because as I told you, the natural time scale is a fraction of nanosecond. The overdrive can be anything between 0 and a few units. So this factor will be from 2 to 5, and if you try to go to smaller values, you will break the junction. And the standard deviation of the tilt gets in the logarithm if you look at the switching time. So even if this is a big number, in the end this is going to be typically 5. So if you multiply all these factors, you can understand why the switching time in STT-MRAM is of the order of a few nanoseconds to 10 nanoseconds in that regime where you have a substantial overdrive. But the time scale of the switching is not the only thing you're interested in. because you have to co-optimize the switching voltage and the switching time. So if you wanted to reduce this switching time, you would like to reduce this natural time scale, but this would mean increasing alpha, which is forbidden by the optimization of the switching voltage. Okay, you would like to optimize the applied voltage, of course, and one way to accelerate the switching without compromising the voltage that you need is to increase the effective anisotropy field at the expense of the magnetization thickness product. Because if you look at the VC, then if you increase HK and decrease MST, you see that you will not modify VC. But since in the natural time scale, which is the reciprocal of the half-line width of FMR, you increase the effective anisotropy field, then you will indeed accelerate the switching. Okay? So that's why there's a lot of research on trying to get free layers that have high anisotropy and low moment. This is because for the same switching threshold, you can have a faster switching. Provided, of course, you can do this material trick of getting high anisotropy and low moment while maintaining the other properties. Okay, so one strategy is, for instance, to add dopants inside the iron-cobalt boron layer, dopants that are not magnetic, so that you would reduce MST, but that yield anisotropy. So, for instance, if you put tungsten, this increases the anisotropy of the system. And of course, the thinner is the better, because you always pay the price of demagnetization energy that reduces the overall anisotropy. So that was for a macrospin, but as I told you, there's no STT-MRAM that switches fully in a macrospin manner. They all involve domain wall dynamics. And if you remember the magnetization dynamics, there's a stage at which the magnetization stays coherent, so this time can be described in the macrospin approximation, and a second stage in which there is a domain wall that sweeps through the sample at a constant mobility. So the time it takes for switching will be the sum of a macrospin time and a domain wall sweep time. So the macrospin time is still this 3 to 10 nanoseconds that I described earlier. And then there's many ways to calculate the switching time, so the part that is due to the motion of the domain wall through the device. Okay, and essentially the one I prefer is this one, where, because it evidences that the natural timescales comes also in this part of the switching time, and the other terms are, of course, how much voltage you apply. Okay, and note that this is a 1 over V factor, while for the macrospin dynamics it was 1 over V minus 1. So this term 1 over V decreases faster. Okay, and then it's the ratio of energy barrier and the energy of a block point. Okay. But if you look at the numbers for this, this only gives you 1 to 3 additional nanoseconds, depending on the size of the junction. So that in the end, the switching time of even in the domain wall dynamics, is given by the natural time scales. And what you have to do to accelerate the switching is really to reduce tau. Okay. And so once again, this is increasing the anisotropy at the expense of the magnetic moments. So get high anisotropy and low moment free layer, and also have them robust enough to be able to increase the voltage without breaking down the junction. And I want to mention that the exchange stiffness of the free layer doesn't play a substantial role, because it's in the second blue factor. Okay, and so it's only a minor fraction of the switching time. Okay, and this tells us that in fact there's no reason to try to do anything else than iron cobalt based alloys to get a fast switching, as long as the switching stays with a domain wall process. Of course, if someday we have a macrospin behavior because we are small enough, cold enough, or just small enough, then there will be an interest to investigate other materials. And so this brings me to the third part of my talk. So I hope I convinced you that the main parameter we should work on is tau, the natural time scale. And so you can play on the anisotropy and play on the magnetic damping. And so for me this is the most interesting strategy. This is reducing the damping of the free layer. So I will spend some time describing how we get to low free layer damping. So the numbers of for the damping of iron cobalt alloys, if you have very good single crystals in the bulk state, then there will be a few times 10 to the minus 3. Okay. But in practice, in thin films, you can have this value up to very large numbers. So as a rule of thumb, the nominal composition is not very informative of the damping. There's a large variability of the free layer damping, and even for nominally identical materials, and there's a lot of variability of the damping of the free layer. And so now I want to understand why there is this variability, and so what to do to get always low damping for the free layer. And the first thing I want to comment on is how the boron content impacts the damping. So, but first let's describe how we measure the damping parameter. We do it by so-called vector network analyzer ferromagnetic resonance, which is a technique where you take your tunnel junction, you put it on top of this yellow strip line, and you flow some RF current into it. So the RF current sees an impedance, and this total impedance depends on the permeability of the magnetic layers, so that if you can frequency resolve the impedance of this ensemble, you can frequency resolve the permeability of the magnetic sample, and the frequency at which the permeability resonates will give you the anisotropy of the free layer and the field that you apply, which in principle is something you know, while the width of this resonance of the permeability, so the ferromagnetic resonance, will give you a measurement of the damping factor. So let's use this tool to characterize iron MgO, iron cobalt boron MgO tunnel junction. Okay, what's the ideal material structure that we dream of for STT-MRAM application? The ideal material structure we want is something where the iron cobalt layer is perfectly crystalline, the MgO is perfectly crystalline, and there's a perfect epitaxial relationship between these two. And if you have this, you're going to have a high magnetoresistance, and you may hope to have a low damping, just like in bulk single crystals of iron cobalt. Unfortunately, when you deposit the layers, you have to deposit them on 300mm wafers, and the only way to get something that is very smooth is to deposit the layers in the amorphous state. And in this case, you have absolutely no TMR. So in order to try to pass from the amorphous state as deposited to the ideal state, what people do is they anneal their layer. Unfortunately, when you anneal, you end up with two problems. Of course, you crystallize, okay, but in the end, you can have some roughness at the interfaces, and you can have interdiffusions of dopants within the free layer, which degrades your TMR and your damping. So you do have two problems to solve: the roughness at the interface and some interdiffusion. And for the roughness, I advise you to look at this paper of Johan Svert and co-workers. I will only focus on the interdiffusion. And the interdiffusion comes from the thermal budget that is used to prepare STT-MRAM devices. So, because STT-MRAM is embedded into CMOS, it has to undergo the CMOS back-end of line annealing, which is 400 degrees C for a long time. And there's absolutely no negotiation possible with this thermal budget. So when you anneal this as deposited state, it will crystallize at a given temperature that depends on the boron content. And what I want to stress is that at the moment of crystallization, the interfaces are probably very abrupt and very well defined, because when you were in the amorphous state, the atoms had no mobility, otherwise they would crystallize. So they had no mobility, so there was no way of getting interdiffusion before crystallization. Okay. But so the crystallization happens at some temperature and you go on annealing, so which unfortunately triggers interdiffusion, which is harmful for the TMR and for the damping. So the solution for that is to try to avoid this second step of diffusion. And the button that people play on is the boron content. Because in fact, if you increase the boron content inside the free layer, you increase the crystallization temperature. And this is, by the way, this is a trick that most people from the metallic glass community use. If you increase the content of metalloid in a metallic glass, you tailor the crystallization temperature. But if you go to, for instance, 30% of boron, then the crystallization temperature gets very close to the temperature of the back end of line anneal. So if you are in this situation, then essentially you can almost avoid the last step, which was the interdiffusion. So you play with the boron content to postpone the crystallization as much as possible to block the interdiffusion much longer. Okay. And if you do that, you can hope to be in the ideal material structure at the end of the back end of line annealing. So to test this strategy, we made an experiment, a didactic experiment, which is the following. We take three layers that are similar, with the except that they differ by the boron content. And I'm sorry, the boron here in green should be inside the blue iron cobalt boron layer. Okay, so the graph is wrong. And when we do that, we anneal at 400 C, and then we characterize the stacks. If you look at the usual performance metrics, tunnel magnetic resistance, array, these two samples with 20% of boron on 30% of boron are very comparable. But if in contrast you look at the damping, so you look in practice at the line widths of ferromagnetic resonance, you immediately see that it's much more narrow for 30% of boron than for 20% of boron. And this is just indicative that the damping parameter is better, and most probably because there is less tantalum contaminants inside the stack. So although engineering the boron content allows to reduce the damping parameter, it's still higher than the value that was obtained for cobalt iron. So a second thing that we can do to reduce the damping parameter of the free layer is to switch from single MgO free layer to dual MgO. That is to say, to compare a situation where the free layer is sandwiched between the tunnel oxide and a tantalum cap, for instance, and the dual MgO situation, where the free layer is sandwiched between two MgO layers. And unfortunately, it's not as simple as this, because we need to maintain a thin tantalum or tungsten spacer at the middle of the free layer. And the reason is that when we anneal from the amorphous state, the crystallization front comes from the MgO interface towards the inner side of the free layer. So there's two crystallization fronts that might meet in the middle of the free layer. And in order to avoid to have a grain boundary at the middle of the free layer, that would be very detrimental to the performance. We had this glue, which is this small, this thin spacer, in this case of tantalum. Okay. So let's compare the damping parameter of a single MgO free layer and a dual MgO free layer. So for this, we conduct VNA FMR on a full stack. So since it's a full stack, at a given applied field, you see many resonances ranging from 30 GHz to 70 GHz, and they come from the different layers in the stack. But the one we're interested in is the free layer, which is the one that is the most narrow. Okay, and so if we zoom on the permeability, we have these kinds of curve with a given line width. If we now do the same sample but with a dual MgO free layer, you see immediately that the line width is better. Okay? And so you can, if you deduce the damping parameter, you can see that in this dual MgO3 layer, even after the annealing, the damping is below 4 times 10 to the minus 3, which now is not that bad compared to perfect perfect iron cobalt single crystals. So what you've seen is that by going from single MgO3 layer to dual MgO, we've reduced the number of heavy metal contaminants or potential contaminants, okay, and this reduces the damping substantially to a very good level. And if you want to be more convinced, you can do the following experiment. You can vary the thickness of the tantalum spacer at the middle of the free layer, calculate the damping, measure the damping for a few thicknesses of tantalum, and you will see that it grows as the number of heavy metal potential contaminants inside the stack. And so this brings me to the summary of my talk. That was about the switching paths in STT-MRAM and the key parameters that could be used to engineer the switching paths. I spent some time explaining the macrospin switching process because the VC, so the threshold voltage of macrospin, is a relevant parameter even when the reversal is very non-uniform. And the natural time constant of the macrospin approximation, tau, is also a very relevant parameter because it affects also the speed of reversal when it's a domain wall-based process. So in order to optimize these two parameters, one main ingredient is to reduce the damping parameter as much as possible. And for this, one way is to play on the boron composition, to postpone the crystallization as much as possible and avoid interdiffusion. Okay. Another message is that every atom of heavy metal contaminant that you can spare within the free layer will bring an immediate benefit in terms of damping, so in terms of switching threshold. Okay, and same also if you can reduce the moment by reducing either the number of spins or compensating them in some ways, you will increase the anisotropy and decrease the magnetization, which will yield the speed benefit. And of course, one last thing that you have to do is to work with the lowest array product possible. Okay, and here are some references that describe a large part of what I've been talking today. And with this, I thank you for your attention.